Welcome, math professors. Our YouTube channel covers topics that can be found in any college math class. So today I'm going to do flux across a simple closed plane curve. So if you like our free content, please consider liking, subscribing, and sharing. It'll help us grow our channel. So if C is a smooth, simple, closed curve in the domain of a continuous vector field F in the plane, and if N is a normal, outward pointing normal vector on C, then the flux of F across C is defined by this. So the flux across C is going to be the integral over C of F dot that normal vector ds. So looking at this, I've kind of drawn it flat because we're really talking about this thing being in some kind of plane, and we'll see why that's the case in a second here. So what I want to know is, in the previous video we did work done. So if I look at like a point on this spot right here, and this was like wind, I can see that point would be moving around because the wind would be blowing the point across the train tracks. But in flux, we're more talking about what happens like against the curve. So more importantly, like when we look at flux, we kind of look at like pressure vessels, for instance. And if I want to know, like I really need to know what is the outward push of that of the stuff inside on that particular pressure vessel, because if the outward flux is more than the material strength, then that pressure vessel is going to fail. So that's kind of what we're looking here. We want to see what is the force against the curve as opposed to with the curve. So this is against the curve as opposed to with the curve. So when we're looking at these normal vectors, I can see that each one of these normal vectors on this particular green curve is going to be outward this way. So we're talking about these outward normal vectors, and so on. So now what I need to do is I need to dot it with these things. So I'm really actually asking when these things are pushing against it. So how is this thing calculated? So let me kind of set it up and show you. All right, so here's the setup. What we know is we're talking about a curve that is in a plane. So we also talk about a simple curve. What we mean by that is a simple curve has to not look like something like that. Even though this is closed because it reaches itself, it's not simple because of this reason. So closed simple means it has to be closed, and then it also has to be simple with none of those loops in the middle. So something like that is also not considered a simple curve. So we're talking about this closed simple curve here. And really what I want to do is I want to get this into a workable integral. So I need to know what f dot n ds can get into, because really what I want to do is I want to have the integral from a to b of something dt instead. That's kind of what I'm going for. Okay, so so in order to do this, I have to find n. I know it is going to be the cross product between the tangent vector and then also the k vector. Remember that this thing is in a plane, right? So k is going to be straight up. So let's do those cross products. So t cross k. Well, t is going to be the differentials of the derivatives of r with respect to the curve. So dx ds and dy ds, and then 0 because this is in that plane. And then k is going to be 0i plus 0j plus 1k. So that's k. So now when you do their cross products, you do the determinant of this matrix. So covering up the I, it's going to be dy ds times 1, which is dy ds minus 0i, and then minus dx ds times 1 minus 0, and then that's going to be j. And then finally we can see when you want to do k, when you cover this up, this times this is 0, this times this is 0, so that's why we get 0k. So we really can just kind of erase the k here when I'm working with, over here when I'm working with this dot n. So I know that f is going to be equal to mi plus nj, so if I want to do f dot m, mi plus nj dotted with this, I left the 0 component off because there's a 0 over here as well, so 0 times 0 will be 0. So this is going to be, the dot product is going to be multiply their first components plus the multiplication of their second components. So finally, when we have the integral over c of f dot n ds, this is going to be the integral over c of, well, f dot m is going to be m dy ds plus n dx ds, sorry, minus, should be a minus, yep, this is minus, so this is minus ds, all ds. So you can see that these the s's are going to disappear. So this is going to be, we'll say the integral from a to b, but we can even say the curve here. So this is the integral over the curve of m dy minus n dx. So it has that very similar differential form that I showed you with the work integral. So we're going to do an example that does both the outward flux across that and then also the work across two particular vector fields and see if these, these values make some sense. So let me set it up. So what I want to do is I want to find both the flux and the work done on these two particular fields. So here's going to be, the field that looks like everything's exploding the radial field, and then this is going to be the field where we have this circulation. And I want to do this on the unit circle. So cosine I plus sine, cosine ti plus sine tj from 0 to 2 pi. So we're talking about a unit circle here, something that looks like this. And then similar, a unit circle here is going to be something that looks like this. And I want to talk about the work done and also the flux across these closed simple curves. All right, so let's do it for the very first one. So let's find the flux first. So find the flux, outward flux. I'm just going to say flux for shorthand. So what I know is this is, in order to do this, I'm going to need to know an m, a dx, an n, and a dy, just like I have to do with work as well. So what's nice is when we set these things up, we'll be able to do them both very quickly. So if I want to do this, I know that m for this particular field is going to be that coefficient function, and then n is going to be equal to this coefficient function. Now I have to define these on the on the curve. So the curve, which is x, is going to be equal to the cosine of t, and then y is going to be equal to the sine of t. So remember that this is the force has to be defined on the curve, so these have to go into here. Also, well, that would mean that m is going to be equal to the cosine of t because I'm plugging x in here, and then n is going to just be equal to the sine of t because I'm plugging y into there. Now I also have to find dx and dy. Well, dx are these differentials, so the derivative of the cosine, or the differential of the cosine, is minus sine of t dt, and the differential of y is going to be equal to the cosine of t dt. So now I have all the stuff that I need to do. So I know that the flux over C is going to be equal to the integral from 0 to 2 pi of, we know the flux is going to be here, it's m dy, so m is going to be the cosine of t, dy is going to be the cosine of t dt. Now what I'm going to do is I'm not going to put a dt over here, I'm going to put them all over here, okay, I know that I can do that. Minus n, which is sine of t, dx, so this is going to be sine of t times dx, which is going to be minus sine of t, dt over here. So what we get here is this is going to be cosine squared of t plus sine squared of t, so this is going to be the integral from 0 to 2 pi. Cosine squared of t plus sine squared of t, that's Pythagorean theorem, so this is going to be 1 dt. So this is going to be t evaluated from 0 to 2 pi, which is equal to 2 pi. Now if I want to do the work, this is going to be the integral of a curve, or from 0 to 2 pi, of m dx, so m is going to be cosine of t, dx is going to be equal to times cosine of t, dt, so I'll put it over here again, plus n dy, so n is going to be sine of t, and dy is going to be equal to, boy, this looks off, let's make sure, m is cosine, dx is minus sine, there we go, I got it better, m dx, so minus sine, and then n, which is sine of t, and then we have to do dy, which is going to be cosine of t, again dt. And we can see that these things are opposites, so they'll cancel. So this is just going to be the integral from 0 to 2 pi of 0 dt, which is going to be equal to 0. So, well, let's kind of discuss this, and we'll kind of make some predictions over here before we do that. So what we know is the flux on something really is kind of like the pressure vessel. And right now my vessel is going to be this circle of radius 1. And since this is like that radial field where everything is pushing out, I can see that these field lines are actually going to give me an outward push onto that circle over, over the circle. So on average, I guess the idea is over the circle, everything's going to be pushing outwards. So we can see that over the entire circle, it's pushing outwards at a value of 2 pi. So I'm getting, a positive number because it's pushing, out across that field. Now, what about the work done? Well, if I put a particle here, since everything, since these field lines are always normal to this particular curve, that's why we get a positive value for flux. But since they're all normal, if I put a point here, everything's just pushing against the curve no matter where I get it to go. So that point's not going to move at all. So it's just going to stay in one spot no matter where I put it because everything's always normal. This field's always normal to that curve. So that's why the work done here is 0. Now in hindsight, if I try to ask for this thing, if I ask for its work done, because I know the work done was 0 here, if I put a particle here, this wind, I guess you can call this, is going to kind of move this thing around that circle. It's going to move it, counterclockwise around that circle. So work will be done because that particle will move. But we notice that the circulation here is always tangent to this particular curve. So since all these field lines are tangent to the curve, there's nothing really pushing against the curve. Therefore, we're going to see that the flux is likely going to be 0 here, but the work is going to be a number. So let's find it. So actually, what's nice about this is we could use all these same things. Oh, we don't. That's too bad. But we get close. So let's do it over here. So m in this case is going to be equal to this, so minus y. N is going to be equal to x this time. Now remember, our x is still this curve, so x is going to be the cosine of t, and then y is going to be equal to the sine of t. So now evaluating, the field at this curve means I have to plug in these values. So for the m curve, I have to plug in y. So this is going to be m is going to be minus the sine of t. Make that nicer looking. And then n, I have to plug in x, which is going to be equal to the cosine of t. Now, dx is going to be the differential, so this is going to be minus sine of t dt, and then dy is going to be equal to cosine of t dt. So finally, I can set this up, the flux. The integral from 0 to 2 pi of mdy, so mdy, m is going to be sine of t, dy is over here, so times cosine of t dt, minus, we know it's going to be n dx, so n is cosine of t, and then dx is going to be equal to minus sine of t. Does that make sense? Double check. There it is, minus sine of t. So what we see here is this is going to be the negative sine t cosine t, it's the minus here, and then this is going to be negative times a negative, which will be positive. So these things will annihilate to 0. So this is going to be the integral from 0 to 2 pi of just 0 dt, which is going to be 0. So it really reinforces the idea that this has no outward push, so it has no flux. And then our work. So remember, it's F dotted with a normal, so it has no outward push. So the work is going to be equal to the integral from 0 to 2 pi of, well, this is similar, so it's m dx, so minus sine of t. Dx is going to be minus sine of t dt plus m dy, or n dy, is going to be cosine of t times cosine of t, again, dt. So this is, again, sine squared plus cosine squared. So this is going to be the integral from 0 to 2 pi of just 1 dt, which is going to be equal to 2 pi. So that gives us an idea of both what work and flux do on these closed curves. So if you like the content, please, again, consider subscribing and liking. So I'll see you in the next video.